Okay. Oh, oh, we got this. Good morning, everyone. So we have today class 8. We have the second class on Sparkle. So we're going to speak this time about the new features in Sparkle 1.1. So the last time we started to talk about Sparkle, and we're going to focus on the 1.1 part of the language today. So Sparkle 1.0, the language we already covered, was proposed or recommended as a standard in 2008. Today we're going to cover Sparkle 1.1, which has some cool new features. It was first recommended as a standard in 2013. So there were some features of SQL in particular, but also of other graph query languages that would be very useful in the context of Sparkle. So this working group convened around 2011, 12, 13 to add these new features to the language. So we're going to talk about some of the new features. I'm going to pass kind of maybe quickly over some of the stuff that is very similar to SQL, because you're already hopefully experts in SQL, especially if you took the course with me. Hopefully you learned a lot about SQL in that course. So we're going to start with negation. Yeah. So negation in SQL is minus or not, or sorry, is not exist or except. In Sparkle 1.0, we have without any explicit negation feature, and this is a big hint for, although the lab is now over, of how to answer one of the questions. We already saw this in the class. We can use a combination of optional and not bound in order to specify negation. Yeah. So this is question 8, I think, in the last lab. So how do we do this? We say movie is a movie, and we look for optional movie first air date, and then we apply filter not bound date, which effectively finds us the movies without a date. Yeah. So we have some explicit negation features as well in Sparkle 1.1 that don't require these strange tricks in order to specify. We can do filter not exist, where we say movie a movie, filter not exist, movie first aired date. So we're looking explicitly again for movies that don't have a first air date. So filter not exist we can use, and the second option is to use minus. So with minus, we just say movie a movie minus movie first air date, and it will return the same result. Yeah. So this allows us to find cases where things don't exist. Yeah. They're almost the same. So you might ask, why do we have two ways to express the same thing? And this is a very common question in Sparkle. What are the differences between minus and not exist? They're almost identical. There are some minor differences. I think this color is off here. There's one. The hat. What else? Flower. Any others? Flower, hat, this thing. I'm sure there's more. Okay. So what are the differences between minus and not exist in Sparkle? So not exist returns results if the pattern on the right has no matches when replacing variables from the left. So it's actually not well defined. This was learned after the recommendation that the way not exist is specified in the standard is not well defined in some cases, but okay. Minus, so this removes solutions from the left that join on the right with at least one variable in common. So the definitions are a little bit messy. Yeah, it would be good to get some database theory people in to help define this sort of stuff. But okay, we'll have a look at an example. It's still pretty difficult to understand or to spot what the difference is to be able to distinguish the two. So we'll show an example. It's in any case the differences are really they're really just limited to specific scenarios. That's one specific scenario is the most common. So we have a query here, which is movie a movie, and filter not exists, S a series. Yeah, so S being a variable. And we see this query is a little bit weird because there's no variables in common between the outer part and the inner part. Yeah. In this case, we have the same query, but this time we use minus rather than filter not exists. Okay. So what's the difference here? So in this case, the semantics we apply, we say if there exists any solution for this thing here, and we replace whatever variables from outside with inside the filter not exists. If there does not exist any results for this, then we return the result. If there exists a result, we do not return it. So the thing is here, filter not exists. We ask, does there exist a series? Yes, there is a series. There it is. So therefore it exists. So filter not means that we don't return anything. Yeah. So we have empty results. In this case, we remove anything that joins, something called an anti-join. But there's an additional rule in minus, which says that, okay, well, if there's no variables in common, that also doesn't count. Yeah, so we don't remove anything. So we need to have at least one variable in common, and we have to then avoid a join. So in this case, there is a match, so we return no results here. In this case, we'll actually return Sharknado and Sharknado 2 because there's no variable in common. It doesn't affect anything. It's redundant. Yeah. So this is a little bit weird. In any case, the examples where it's different are also a little bit weird. It's kind of a strange thing to have a minus or not exist where there's no variable shared with what's outside it. So in this sort of obscure case, there are differences, but for most cases, they're almost identical. So this is the two new explicit negation features in Sparkle. One thing that's okay, that's similar to SQL. One thing that's very different from SQL and from relational databases in general, and are very common in graph databases, are property paths, allowing us to define our queries over paths of in the graph. So we have essentially a language which is a regular expression over the predicates of a path. Yeah. So this allows us to define essentially queries that can return for us the nodes that are connected by paths of length 1 or more, or 0 or more even. So we could have a query that, for example, does a query over length 12, 13, 14, 15 paths, which we couldn't do before, that matches a regular expression. Yeah. So what do we have in our language? We have a predicate, which is just an IRI. We have an inverse path, which we use this symbol for, to say go in the other direction. We have a path of E1 followed by E2, and here E is defined recursively, right? So E1 could be, for example, the inverse. It could also be the what's called a concatenation of something else. We have E1 or E2, which says a path of E1 or E2. So I'll try to give maybe some examples as we go. So E here, let's say E was simply an IRI. Let's say it was a parent. Then inverse E would intuitively give us child. Yeah, it would give us the opposite relation. E1 followed by E2, if we had parent followed by parent, it would be equivalent to looking for grandparents. Yeah. If we had E1 followed by E1 or E2, if we said, for example, father or mother, then it would be similar to parent. Yeah. E star would be if we had parent, star says 0 or 1 matches. Yeah. So if we do parent star, what we're doing is searching the whole ancestry. Yeah. We're also returning the node itself. So if we say Aiden parent star and then some variable, it'll return me, all my parents, their parents recursively. Yeah. E plus is the same, except for if we do Aiden parent plus, then it doesn't return me. It only returns, it's 1 or more, right? So it returns my parents, not me, my parents' parents, and so forth. E question mark is a path of 0 or more, 0 or 1 E. So we could say, for example, we could say if we want to return siblings of somebody and we want to include themselves, we could do sibling question mark, Aiden sibling question mark, which will return Aiden and then all of my siblings. Yeah. So essentially it says, okay, we include the node itself and we also include then whatever the path is. Not P would be essentially every relation, or it would be whatever edge we want, but not P. So we could say Aiden not, it's kind of a little bit strange, but Aiden not brother, and then we would return my sisters and parents and whatever. Yeah. Not P1 to PK or inverse PK plus 1 to PN. This is just a way of doing the same thing, but now we can provide a list of predicates and say don't follow any of these edges. Yeah. And then finally, we can use parentheses for grouping. So we can actually combine these features to do, for example, Aiden father or mother brackets star, which will find all the ancestors if we don't have a generic parent relation, but rather a father-mother relation. So this is a bit different to SQL. So we'll spend a bit of time looking at it with examples. Only these features cannot be rewritten to something else. So if we have E1 or E2, for example, we can rewrite that to a union. There's nothing really new. And actually, that's how the Sparkle standard defines it. If we define E1 followed by E2, we can also do this by doing a join variable. Yeah, so we could do, and rather than parent followed by parent, we can do aiden parent variable P, parent P2. Yeah, so there's nothing new in expressivity. What is new here is the asterisk and the plus. So this is called clean star. I don't know if you've heard of clean star before. It's this operator that allows exactly this, that in a graph it allows you to look transitively across a certain path. And the clean plus, which is one or more. So these features give us something new. They give us something new because now we can query for arbitrary length paths, which we cannot do before. Okay, so we'll take one example here, which would be an RDF list. So we're going to ask which movies are in the Sharknado series. We have an RDF list. So we have Sharknado series, movies, first Sharknado, rest, first Sharknado, rest, first Sharknado, rest, nil. Yeah. So what we could try to do is to write out this, let me see. Where is my alt? Escape. Where's my video? Here I am. Okay. Let me see. Here? Am I here? Should do. Okay. Yeah, so we can try to write out this this query pattern. Yeah. So we have Sharknado series. And what we'd like to do now is to oh, it doesn't look so good. Hopefully it's relatively visible. So what we'd like to do now is return Sharknado, Sharknado 2, Sharknado 3, and we're not going to assume that the list is of a finite length. We don't know, well, it's going to be of a finite length, but we don't know it's not going to be of a bounded length, right? We don't know how long the list is going to be. So what's the first thing we need to add to our property path? It would be the very first predicate, which is movies. Yeah. And then we need to choose the next thing that we add to our property path. Any ideas? Would it be an or? Would it be a star? Would it be a plus? Would it be a star? Okay. So if we do star, what we'll have here is 0 or more movies. So if we have movie, we could follow several of them. So in fact, we could keep star here, but we don't need it. It won't be so helpful. Because we can assume here that we have movies that points to the start of a list, and then we need to navigate the list. Yeah. So what would be the next thing? What? It would be followed by, yeah, this slash here, which means okay, followed by movies, followed by something. Yeah. So what is the next step? If we want to get to Sharknado, we need to follow it by first. Yeah. So we could do RDF first. Yeah, so this will get us now, and then put a variable here. What's the movies? Okay. So what will this get us if we leave it like this? This will only get us Sharknado. Yeah, so it's movies followed by first. Yeah. So how could we get to Sharknado 2 and Sharknado 3 here? So we need to navigate rest somehow, right? So we could do, let's say, followed by RDF rest. Yeah. And then put a star, something like that. Is that good? So it says movies followed by first, followed by rest, but we have no rest here, right? So how would we fix that? And then do first, right? First here, yep. Oh no. Changing the position. Yeah. So we need to do it this way, right? So we need to do rest, star, and then RDF first. Yeah. So now we have movies, and then we say followed by 0 or more rest. So that's okay. This satisfies the 0 or more rest, followed by first, which gives a Sharknado. But also, if we have 0 or more rest, we can go here and then go to Sharknado 2, and we can go here and go to Sharknado 3. Yeah. So this gets us what we're looking for. Okay. Okay, so here's the results, here's the query, and here's the results. Oh, I had the answer here all the time. All right, okay. Oops. Fine. So here's the results. We get Sharknado, Sharknado 2, Sharknado 3. Okay, so this is an example. This is one of the use cases for property pots to be able to navigate lists and extract all other elements. Here's another example. We're looking for the finite Bacon number. The people who have a finite Bacon number. So have you heard of Bacon number before? Kevin Bacon number? No? Kevin Bacon is an actor who has acted in a lot of movies with a lot of people. Yeah. So there's this thing called the Kevin Bacon number, where if you're Kevin Bacon, your number is 0. If you acted directly with Kevin Bacon, your number is 1 in the same movie. Yeah. If you've acted with somebody who has acted with Kevin Bacon and you don't have a Bacon number of 1, your Bacon number is 2, and so on. Yeah. So in this case, we know that Tim Robbins, we know that Kevin Bacon has a number of 0. We know that Tim Robbins has a number 1. We assume that Meg Ryan has a number 2. She might have a number 1 if she acted also elsewhere, but we'll assume here that it's 2. And Nicolas Cage, we would have a number of 3, Kevin Bacon distance from this. Yeah. So it's similar to the Erdős number. If you've heard of Erdős for mathematics or also for computer science, people talk about the Erdős number, which is if Paul Erdős, if you wrote with him, you have an Erdős number of 1. If you wrote with somebody who wrote with him and you didn't write with Erdős directly, you have a number of 2, and so forth. So this is Kevin Bacon, and then there's the Bacon Erdős number, which is the maximum of your Bacon and your Erdős number. So there are some people with finite Bacon Erdős numbers. So who has a finite Bacon number? So what we're looking for here is basically we're looking for Tim Robbins, Meg Ryan, Nick Cage, anyone who's connected to Kevin Bacon. Yeah. So we can try this again. See, I should have just left it here. Okay. So we're going to try this one again. So we have Kevin Bacon. And we would like to query, to use a property path to get from Kevin Bacon to Tim Robbins, Meg Ryan, Nicolas Cage, and so forth. Yeah. Any suggestions on where to start? Actor or actor? Actor, okay. We have actor or actress. Yeah. So what would we like to do with actor or actress from Kevin Bacon? One thing that we should note here is that we're actually not going in the forward direction of the edge. We're going backwards. Yeah. So we need to invert that. So that would be inverted. We could do invert here, or we could do invert here, but what I'm going to do is just put this in parentheses and invert everything. So inverse actor or actress. And then what else do we need? Forward. Board, yeah, okay. Followed by actor or actress. Right? Okay, and what else? So what we've done now, what we have now is we can get from Kevin Bacon to Tim Robbins. Yeah. And then what would we like to do? Another time. So we could do followed by and then write this again. Yeah. But there's no need to do that, right? So what we're going to do is use the star. Yeah. We can use the star or the plus. We can talk about that. Finite Bacon number, FB. Yeah. Okay, so we have inverse of actor or actress, which gets us from Kevin Bacon to the movie Mystic River, then forward to the actor or actress, which gets us to Tim Robbins, and then we do that recursively. Yeah, so it means that from here we can also navigate to Top Gun, and from Top Gun to Meg Ryan, and this is another result, and then back through actress City of Angels to actor Nicolas Cage. Yeah. Okay. So here is our query, just as we wrote it on the board. And here's our results. Yeah. So what's of note here is that we get Kevin Bacon because everything here is a star. Yeah. So star means 0 or more. So actually Kevin Bacon himself is included in this result. What would happen if we replace the star with plus? How would the results change, do you think? Yeah, so one idea would be that Kevin Bacon would disappear. In fact, he won't disappear in this case. Yeah, kind of a bit strange, but what happens is, yeah, so essentially we can get from Kevin Bacon to actor and then back to Kevin Bacon. So we can reuse the same edge twice if we want. Okay? So we do have a length longer than 0 path back to Kevin Bacon. Yeah, we have a length, let's say a length 2 path, we could say, right? So from Kevin Bacon to back, inverse actor, and then forward to actor again. Yeah. So this actually, if we think about it, there's an infinite number of paths from Kevin Bacon to Kevin Bacon. Yeah, because we can go back and forward as many times as we want to Mystic River. Yeah. So are our results finite is the question in this case. So we have to be careful when we have paths in query languages. We have to think, do we have a finite number of results? And the answer is that since we're only returning nodes here, we're not actually returning edges or the full paths themselves. It's finite. All that we can return here at most is all of the nodes in this graph, and that's always the case. Yeah. If we have 2 variables, if we have a variable on one side and a variable on the other, then we can have at most node times nodes results. Yeah. So we have finite results because we're only returning the endpoints of the nodes. It would be super useful to be able to return the paths sometimes, and there are languages that allow that. And the most common semantics is either shortest path, where you only return the shortest path between 2 nodes, or simple path, where you return all of the paths, but you never repeat an edge. And with that, the number of simple paths can be exponential, but okay. So this is property paths. It's a pretty widely used feature. It's very commonly seen in query logs. Lots of people use it. It's very common, for example, for doing RDFS kind of inferencing. So it kind of cheats, and you can just put RDF type / followed by RDFS subclass star. And that way you can do like subclass reasoning in RDFS, for example. That's another common use case. So it's a very useful feature that's quite particular to Sparkle and other graph query languages, not something that this sort of query would be much more difficult to express in SQL. You do have recursive SQL that can do this sort of stuff, but it's not nearly as intuitive. Okay, so we cannot actually get the length of the path. We cannot return the path, so we can't get the actual number, but we can at least get the people who are connected via such paths to Kevin Bacon. Any questions or doubts about that? No? Okay, so our next feature is query assignment, or variable assignment, sorry. So it's more of a syntactic feature, but it's quite useful. We can use this feature called bind if we want to do some sort of calculation and store the result as a new variable. Yeah. So in this case, we have movie first air date, and then we say we're going to bind the cast of the int of the substring of the date between 1 and 4 as year. And we're going to return the year as well. So what does this do for us? It essentially extracts the year and returns the year as an integer. Yeah. So we get here movie Sharknado, and we get the year 2013. So we can do some calculation using Sparkle functions and then save that as a new variable. Yeah. This here has to be a new variable. This cannot be in scope. It cannot be seen elsewhere in the query. So we can also do assignments with values, which is very useful in a particular use case. As we'll discuss later, we often want to query endpoints via the web. Yeah, we want to query Sparkle data sets via the web. What values allows us to do is to send a bunch of partial solutions with one query. So rather than having to query, give me the capital of Chile, give me the capital of Peru, give me the capital of, and send them all in individual responses, we can use values, for example, to just list all of the values that we're looking for capitals for. So values allows us to specify certain partial solutions that we want to extend by querying the data. So in this case, we're looking for movies and their stars. We have this special keyword called undef, which is like a null. And we have Tara Reid, and then we have Sharknado 2 undef. So what this is asking us basically to do, it's going to take these results here and do a join with the results of movie star star. Yeah. So if we look at movie star star, we should have from our graph Sharknado Tara Reid, Sharknado Ian Ziering, and Sharknado 2 Ian Ziering. Yeah. So what we're asking for now is which movies does Tara Reid star in? Yeah. So which movies does Tara Reid star in according to the data? Sharknado. Yeah. So we have Sharknado Tara Reid, and then we have Sharknado 2 undef, which is equivalent to asking who stars in Sharknado 2, and that would be Ian Ziering. Yeah. So we get these results here. So the undef is like a null again. So if we can fill in those data from the query, we will. So what is the operation here? The operation here is a join. It's just doing a classical relational join. Yeah. Between these results here and the results generated from this table here. Yeah. So values is very useful if we want to query, let's say, a web service, and we want to query for 1,000, something similar for 1,000 different things. Like, what are the stars of these movies? And we have 1,000 movies. Rather than sending 1,000 requests, we can put them all into one values and send them as one query. So we do not get a result for Sharknado Ian Ziering because that result from this part of the query here, we have Sharknado Ian Ziering as a binding or solution for this part here, but it doesn't match, it doesn't join with any of the partial solutions we have here. Yeah? So because Ian Ziering does not match with Tara Reid and Sharknado does not match with Sharknado 2, so we don't get that result. Any questions or thoughts? Okay, so we're going to go to aggregates, and aggregates I'm going to go through kind of quickly because it's almost like SQL. Yeah, so we can do very, very similar stuff to what we've already seen in SQL. So how many movie stars are in the data? Here we want to see how many values there are for stars. Yeah, so we can just write our query, movie stars, star is a variable, and then we can use this count feature in the select. And we can do count star as count. And how many do we get? 3. Yeah, we get 3. So we get 1 here, 2 here, 3 here. Yeah, because there's 2 solutions that witness Ian Ziering. So we get an answer of 3. So if we want to get the distinct count, if we don't want to count Ian Ziering twice, even though he stars in 2 movies, we can apply distinct. Yeah. And in this case, what answer will we get? No. We get 3. Yeah. So it's the same trick as in SQL. We need to be a little bit careful. What does this distinct here do? If we do select distinct, what it says is get rid of all the duplicate answers. Yeah. So we're taking these results as a base, and then we say get rid of all the duplicate answers. Are there any duplicate answers here? No, it's just 3. The number 3 is the result. It's not duplicate, right? So we don't do anything here. If we want to get the distinct, if we want to get a count of 2, so the distinct here would be applied after the count. If we want to count some distinct elements, we need to add the distinct inside the count. And this then will give us 2, yeah, the expected answer. So this is similar to SQL. How many stars does each movie have? If we wanted to do that in SQL, we would use, as well as count, we would use group by. Yeah, so here in Sparkle, it's the same. We just group by movie, and then we do count distinct. So we can use group by as well, and we get here Sharknado has 2 stars, Sharknado 2 has 1 star. Give me movies with more than 1 star. Yeah, so there's several ways to write this, but we could do it with aggregates. So we could take these results here, and then what we're looking for is to filter the movies that only have 1 star. Yeah, so how do we do this in SQL? Not filter, something similar to filter for aggregates. Do you remember what it's called? It's like you can filter after. The problem with filter here is that you would put the filter inside the where, but the count is outside the where. So there's no way for the filter to see the count. So you could do filter with subquery, actually. Yeah. But there is another way to avoid a subquery, which is having. Yeah. So we can say having. So much like in SQL, having a count distinct star greater than 1. So having is basically just a filter, but we can add it to the end of the query and it can apply over the results of aggregates. Yeah. So in this case, we get Sharknado 2. So this feature is not so widely used because people tend to forget about it and they just use a subquery, which is also fine. But we have the option for having as well in Sparkle 1.1. Forgotten in SQL as well sometimes. So these are the aggregates we have in Sparkle 1.1. We have count, sum, min, max, average, group, concat to concatenate a bunch of strings together. And we can apply as well as sample to just take one value out of each group. So in this case, we have maybe just to look at one other example aside from count, we have sample, and we're saying for each movie, what we'd like to do is group the movie and take some star as a sample. Yeah, just take an example star for each movie. So we're only going to have one result per movie. And then we add having count distinct star greater than 1. That's kind of strange. Oh, okay. Okay, yeah, fine. So yeah, we add having count distinct star greater than 1. So we're counting the original stars, not the sample stars, because then there would only be 1. So we're only including Sharknado because Sharknado has 2 stars, and then we sample one of the stars, and that would be Tara Reid. Yeah. So sample allows us for each group, in this case for each movie, extract one value, in this case 1 star. So this could be Sharknado Tara Reid or Sharknado Ian Ziering. Yep. So either is perfectly valid result. So we have some non-determinism with sample. So a quick note on the semantics. When we spoke about OWL, we spoke about the lack of unique name assumption, and we spoke about the open world assumption. So we had this example where we asked how many children does Vito have according to this RDF graph under the open world assumption and the no unique name assumption. And the answer was sort of at least 1. Yeah, because we don't know if the children are different by default, and we don't know if there's more children that don't appear in the data. Yeah. If we run this query in Sparkle, if we ask how many children does Vito have in this RDF graph, what answer do we get? We get an answer of 4. Yeah. So this is this was a big debate in the community for a while. It's like, okay, but why in Sparkle do we get 4 when under the semantics there's at least 1? Yeah. So that's a little bit strange. And some people in here in Chile were writing papers about this topic and saying this is kind of a strange mismatch of semantics. However, essentially how it's defined is basically that, so it looks like Sparkle has a unique name assumption and a closed world assumption. So it looks like if it says exactly 4, it assumes that the data are complete, and it assumes that all of the children are distinct, pairwise distinct, yeah, which it doesn't know here, yeah. So it looks like it's applying a unique name assumption and a closed world assumption, which would be completely incompatible with RDFS and OWL, yeah. However, it's not really the case. So, or at least I would argue the case. So Sparkle does not have worlds or interpretations or models. It does not interpret real people. Yeah. So there's no problem with this query if we just assume that Sparkle is working on the data. Yeah? What do I mean by that? What I mean by that is that Sparkle is counting how many nodes in the graph are in this position. It should not be interpreted as telling you how many children does Vito have. Yeah? And once you understand that, then it's all okay. Of course, if we were to, we could talk about having Sparkle that has a unique name assumption, that doesn't have a unique name assumption, and that has the open world assumption. We could try to think about a semantics for the query language, but it would be a bit boring because the answer for most count queries, for example, would be at least 1, yeah, which might not be so informative, yeah. So the people who defined Sparkle decided that this would work in RDF data directly. It doesn't work on the interpretation, on the idea of, this, how many children does Vito have? It's just saying how many objects are, how many elements are the object of a triple where the subject is Vito and the predicate has child. And in this way, it's compatible, but it's important to understand that. So it's not telling you Vito has 4 children. It's just telling you there's 4 nodes in that position in the graph. Any questions, notes? All good? Okay, so we're going to move to subqueries. Again, it's a feature that's in SQL already, so I won't spend too much time on it. Question here is, how many stars does a movie have on average? Yeah, so if we have to find out how many stars a movie has on average, the first thing we need to do is count how many stars each movie has. So Sharknado will have 2, and Sharknado 2 will have 1. And then we need to take the average over that. So we would expect an answer of 1.5 here. Yeah. So how do we do that? We can't do that in one aggregate, yeah, because we need to count first and then average. Yeah, so these are 2 separate aggregations. So what we can do in Sparkle, much like in SQL, we can have subqueries where we have sub-select queries. The queries have to be selected. We can't have sub-construct or sub-ask or sub-describe. Yeah. So we have a subquery here, which counts for each movie, how many stars it has, and then we have our outer query applies the average over that. And the solutions we get back an answer of 1.5. Yeah, so we can have subqueries. We could also use this rather than having with using a filter. We could have used a subquery and then filter in the outer query the results. So subqueries are very useful when you need solution modifiers or aggregates in the middle of a more complex query. Yeah, so this is pretty common. You can use this as you want, right? But I wouldn't recommend it unless you have this sort of case where you want to do an aggregate on an aggregate, for example. Or you want to do order by and then do something with that. So it's useful when you need something outside of the where, but you need it inside the where, then you can use a subquery. Yeah. Why wouldn't I recommend it in general? Because these queries can be harder for engines to optimize. So you might find that the query ends up being a bit slower. Which movies have more stars than average? So this we would do it in the same way as SQL, of maybe leaving aside window functions, if we assume that there's no window functions in SQL. How would we do this in SQL? And there's no window functions in Sparkle. How do we do this in SQL? Or how do we do this in Sparkle equivalently, right? So which movies have more stars than average? So the first thing would be to count how many stars each movie has. Then we take the average of those counts. And now we need to filter outside again. Yeah, so we need to count the movies again and then see which movies have more stars than the average that we computed. So we have, in this case, the solution has 3 levels of where. Yeah, so it has a subquery and a subquery. So we count how many stars there are per movie. We take the average of all of that, which gives us 1.5, and then outside again, we need to count the stars per movie. And then we can apply a halving to avoid a 4th embedded subquery. Yeah, so we can have subqueries and so forth. Yeah, there's no restriction to that. So here we have Sharknado. There is an interesting part of this query, which is here we mentioned in this subquery, we mentioned movie. And here in this outer part, we mentioned movie. And the question is there any relation between these things, between this variable movie here and this variable movie here? And this is known as correlation in SQL. Yeah. So it's a question of, are these variables, do they have some sort of coincidence? Are they related at all? So the thing we have here is when we have movie here, we don't project movie. Yeah. So a movie is only seen within the subquery. So it disappears. Yeah, it's gone. So the result of this subquery will just be a variable with count and the value 2 and 1. Yeah, we forget about the movies. So then we take the average of the count. So then we lose the count as well. We just can see average outside. So when we come out here, we can't see movie and we can't see star. These are internal to the subquery. So there's no relation. If we change the names of these variables here, if we put movie 1 and star 1, it changes nothing in the query. Yeah. Is that okay? Because they're projected away. Yeah, we just drop that column. So by the time it comes to the outer query, this is like a fresh variable that's not been seen before. Okay, so there's no correlation between movie here and movie here. There are star here and star here. So movie in the subquery is not correlated with movie in the outermost query, and the same is true for star. Okay. So those features are kind of similar to SQL. There's not much different. We're heavily inspired by SQL, right? Because SQL is such a popular feature that it made sense to base the aggregation language on that. A new feature that's new to Sparkle, and not even it's seen in other graph query languages. It's definitely a very distinctive feature of Sparkle is something called federation. And there's been a lot of research around this, and it's largely motivated by the idea of the web of data of this course. Yeah. And this is the idea that Sparkle endpoints are a bit different in that, or Sparkle as a language is different in that the idea is to make endpoints available on the web where people can query them openly, which does not happen with SQL, right? If you worked with SQL before, you've never like opened up an interface where the web could query directly your database, yeah, your relational database in SQL. But this is commonplace for Sparkle. So endpoints are often made public online. So we have this Wikidata query service. Let me see if, yeah, this is the query. So what's the idea of federation? We'll go through an example. I'll have to swap my screen share. Up share. Let me see 1 second. Let me close all this. Okay, and share the browser. Good. Okay. My screen share is loading, but in the meantime, yeah, okay. So we have, this is the Wikidata query service. This is a Sparkle endpoint that we can use to query Wikidata. Some of you may have seen it before. We mentioned that also in the start of the course, I guess. We use it in databases as well. This query is a bit distinctive because what we're doing is a federated query. So what we're looking for here are the Asian embassies in Santiago, in a particular area of Santiago. So what do we have? We have a Sparkle query as normal, and then we have this weird service thing that we haven't spoken about, and this is the federation. So what this service says is we want to query an external Sparkle service on the web, and we want to get some data back from that. Yeah. So within a Sparkle query, we can query another Sparkle endpoint, another service on the web that also supports Sparkle to pull in data, and then we can do joins with that. Yeah. So what we're doing here is we're sending this query to this linked geodata.org Sparkle service, which serves as data about geographical information in RDF and Sparkle. So Wikidata has a bunch of data, but it doesn't have information about where embassies are, like where the Argentinian embassy is in Santiago. It doesn't have that level of information, right? So we're going to rather pull that information from linked geodata. So we're going to ask linked geodata for essentially the points. This is like the locations of certain things of S, where S is an embassy. So we're looking for the locations of embassies. We're looking for the country, what the country code is. So this will give us like IE for Ireland or CL for Chile. And we're asking for a label, like what's the name of this embassy. So we get essentially from this, what we're getting is all of the locations on Earth of all of the embassies and their country codes. Yeah. So, and what we're doing here with this filter is we're saying that this filter, the embassies we're looking for must be at a distance of 10 from this point here, which I've hard coded, which is some place in Santiago. I think it's Baquedano or something like that, some central place. So then to do the Asian embassies, linked geodata doesn't have that information. It doesn't know which country. It just knows that there's an embassy here and it's associated with this country. It doesn't know the continents. We use Wikidata to filter or to query for the continents. So we take the countries that have the same code, yeah, and then we say that the country must be in the continent of Asia. So this might take a while, hopefully not too long. I don't know. Well, I also tried this earlier, so the first time it took about 30 seconds, but it seems I might have cached. So I don't know if it's searching all of the embassies because here we have the filter. So maybe it uses the filter. It actually uses the distance first. So we can have a look and see what we can find here. We see some dots in nice colors, so I'll try to get it to a nice size. Let's see if we can guess. We can have a little quiz. Does anyone know what this embassy is here? Russian embassy.
Russia considered European because Moscow is in Europe?
Both, I would say. Yeah, probably you could check it on Wikidata, but I would say you can kind of consider Russia as both Asia and Europe. But yeah, it's true. Moscow's in the west of the Urals are considered in Europe, and the east of the Urals are considered in Asia. Any ideas here? Indonesia. Let's see where else. We got Syria, Israel, Iraq, Turkey. Any more? Korea. I think that's it, is it? Do you see any more? Okay, so that's the idea. So the interesting feature here again is that we don't have the data in one source or the other, but we can apply a federation for this. This is pretty cool. This idea is very neat, but it has lots of challenges. So one thing is how to optimize these queries. Another thing is how to do joins between data, because linked geodata uses its own IRIs and then Wikidata uses its own IRIs. So it's kind of tricky here. We can use the country code, which is sort of standard to do the join. We can't do the join directly on the countries because one is in the Wikidata namespace and the other is in the linked geodata namespace. So it's a very cool idea, but in practice there are lots of challenges associated with it. So this is federation, and this is essentially the service clause here we see. So let me stop and go back to so you can try that. It's you can try that example as well. It's on the slides. There's a hidden slide in the PowerPoint with that. So we find the Asian embassies within 10 kilometers of Santiago Center. We find the embassies from linked geodata, and then we check the continents on Wikidata. Yeah. There's no restriction to this. We can, of course, we can also have embedded service. So we could say to linked geodata, query Wikidata to find this, and then query that, and then come back and query other things. Yeah.
How do we leave the name of the database we use it as a reference? Like say we're pulling from many databases and we want to say know which answers come from which places.
Yeah, so when we specify which service we want to query, we can use the service here. If we wanted to remember which service or where something came from, I guess one trick would be to use bind. So we can say bind source as and give the IRI within the subquery here. And that would extend all of these results with a new column that says this is the source of these results. Yeah. Yeah, more questions? Or? Okay. So that in general is the query language. So these are all the new features in Sparkle 1.1 for querying. What we have as well in Sparkle 1.1 is an update language, which allows us to change the data, not just to query it. So not just read only, but we can also update data. Yeah. So this didn't exist before, and every Sparkle engine had its own way of like, this is how you insert data and so forth. So this was then standardized in Sparkle 1.1 with this insert language. So what do we have? And I'll go through it kind of briefly because it's sort of more or less intuitive, but there's some documentation here to show different examples. The first thing we can do, the simplest case, is to insert data. Yeah, so we just say insert data, and then we put some triples in turtle syntax. And if we don't specify any graph, this will be inserted into the default graph. So we see here, we say Sharknado series third movie, Sharknado 3, and then we have Sharknado series third movie, Sharknado 3 added to our default graph. If we wanted to insert a triple into a named graph, yeah, this graph is named Sharknado2.ttl. We say graph Sharknado2.ttl, and we want to insert this triple here, and we add this new triple here. Yeah, so we can insert data triples into the default graph, into named graphs, using the Sparkle language. If we want to delete data, we can simply specify the triple we want to delete, and that will be removed from the default graph. Yeah. If we want to remove data from a named graph, we specify the graph name, and then we specify what we want to delete. What about if we want to delete many things, not just a triple or insert a specific triple or remove a specific triple? We can use queries for this. So we can use a where clause to specify to search for something and then delete some stuff associated with that or insert some stuff associated with that. Yeah? So in this case, what we're looking for is the named graph associated with the second movie of the Sharknado series. Effectively, this is what we're doing here. And then into that graph, we're going to insert this triple here, which is movie descriptions, second Sharknado movie. Yeah. So we query for which graph we want to insert this triple into. So in this case, and we're also using the movie IRI as well. We're not just searching for the graph here, but we're also taking the IRI of the second Sharknado movie. In this case, we can do something similar. We can search for the first movie of the Sharknado series, and then we can, from that graph, we can remove its title. Yeah, so we can delete data as well associated with the results of the given query. We can combine insert and delete. So we can, in one command, we can do where to search for some data, then to delete some something associated with that, and then to insert something. So in this case, we're looking for the second movie of the Sharknado series, and we have its graph as G. And we're going to look for its description, and we're going to call that old description. Yeah, its description in the graph. So once we have that description in the graph, what we're going to do is delete that description from the graph. Yeah. And then we're going to insert a new description, which is movie description best of the series. Yeah. So we're going to say here, essentially, we're going to remove the old description of Sharknado 2, and we're going to say this one is the best of the series. Which is, of course, very debatable, which is the best. It's hard to choose between them. So if we want to, we can also use this with keyword, where the graph thing gets a bit tedious because we're always working on the same graph. It's kind of a bit annoying, especially if we know which graph we want to. In this case, it's not applicable because it's a variable. But if we're always working in the same graph and we know which graph that is, which named graph that is, we can just use with Sharknado2.ttl, and effectively that just pretends that it's the default graph from there on. Yeah. So if we insert or delete stuff without specifying a graph clause, what it will do is work with Sharknado2.ttl. Yeah. So in this case, what we're looking for is we're looking for the movie that is titled Sharknado 2, the second one. Then we're going to delete the old description from this movie, and then we're going to insert into Sharknado.ttl a different name graph, Sharknado sequel movie. Yeah, the second one. So we can use with as a shortcut basically for specifying a certain name graph to be the default graph. I don't know that I mentioned it here. Yeah, sorry, I don't know if I call attention to that, but when we do this delete insert where, the order of operations can matter. And what we always do is we search for a where first, then we delete, then we insert. Yeah, so we're never going to delete something we just inserted, just in case. Actually, in this case, it matters because if we were to insert this, then this would delete it, could potentially delete it if it were queried. Yeah. So it's always the query, it's where first, get the stuff, then delete, then insert. Yeah. So you can never delete something you just inserted. Okay, it can be tedious to write delete where So we have the simple delete where the delete clause and the where clause are the same. Yeah, so we can just write delete where, and this is equivalent to writing it out in the full version where we have delete here with this, and where with this, we're the same, the clauses are the same. Yeah. So it says basically we're going to delete what we just searched for, essentially. Any questions, doubts? I thought this was the internet connection unstable sign for a second when I saw it. It kind of looks a little bit like it. Okay, so as some of the last features of the update language, we can also mess around with name graphs. So a very cool feature, again, a very webby feature, is that if there's an RDF document on the web and we want to query it, or we want to build some collection of data that involves that document, we can use this command here, which will load that RDF graph from the web first. So we'll take the RDF graph, parse it, and load it into our Sparkle engine for us. So we just need one command to do that. So what we have here is load, and then we have this optional silent keyword. So the stuff in gray is sort of optional. So silent, basically, it allows us to, if the load fails, to suppress the error. For example, if the document on the web does not exist, then it will throw an error. If we don't have silent, if we add silent, then it won't throw an error. This is useful if we have maybe 100,000 documents we want to load, and if one of them fails, we don't want the whole process to stop. We just want it to keep going. We can add silent. By default, it will give an error. The IRI from, which is like the HTTP often, it could also be FTP, but the IRI, the location of the document we want to load, the RDF document we want to load from the web. We have into graph again, which is optional, where if we don't specify this, we'll load the document, the data into the default graph. If we specify a particular name graph, we'll load it into that name graph. Okay? So the destination graph will be created if it does not exist. And it will fail if RDF cannot be extracted from the source graph unless silent is specified. Okay? So if we can't, for some reason, load or find the document on the web, if it doesn't parse as RDF, then it can throw an error unless silent is present, in which case nothing will happen. So there's a bunch of other features that I'll go through, and they have similar arguments. So we have clear, which can clear all the triples from some graph. So essentially we keep the graph, but we just remove everything that's inside it. Yeah. So we can remove, we can clear a particular name graph, we can clear a default graph, we can clear all name graphs, or we can clear all graphs. Yeah? So just remove everything from the default graph and all name graphs. We have create, which allows us to create a new blank named graph. We cannot create a default graph because we always need a default graph. So there's always a default graph. Yeah, we can clear a default graph to empty it, but we cannot create a default graph. We can create new name graphs, however. So we have create graph and then the URI of the new blank named graph for that. We can drop some graphs, which will remove graphs. So we can drop a name graph, a default graph, all name graphs, or all graphs, default graph and all name graphs. What happens if we drop the default graph? We always need a default graph. It will automatically create an empty one. So essentially drop default is the same as clear default. It just means get rid of all of the data in the default, but we'll continue having a default graph. In the case of a name graph, rather than having an empty name graph, we'll have no name graph. Yeah, it won't exist. Some engines don't distinguish between empty, they don't allow empty name graphs. So in those cases, it won't make much difference. The drop and clear will be the same. Some engines do allow you to have an empty name graph. Copy one graph to another. So basically we can take one, for example, name graph and copy it into the default graph, or a default graph to a name graph, or whatever we want to do. We can copy between different graphs in our data set. Move. So in this case, copy will leave the destination graph as it is. If we do move, it will copy and then delete Copy will keep the source graph as it is. In the case of move, it's like copy and then delete the source graph. Yeah, so we get rid of the source graph. Yeah, so we can copy or move one graph to another. This overwrites the graph that is already there. Yeah, so we're not appending in any case. So if that already exists, the destination graph already exists, it is overwritten. And then add is the option to append the data to the destination graph. So if the destination graph already exists, then we just add the data from this graph to this other graph here. Okay. So we have some ways of managing our data sets and managing data in different name graphs and default graphs and so forth. I went quickly through that, but it's mostly for documentation. So the idea of copying, moving, deleting name graphs is the key idea here. Any questions or doubts? Okay, so we're coming towards the end of Sparkle 1.1 features. One of the cool new features as well that's not part of the query language, it's its own specification, is this idea of trying to connect the Sparkle world with the RDFS and OWL world. So this was formalized through this Sparkle 1.1 entailment regime specification. So what does it give us? It gives us some support for RDFS and OWL entailment. So essentially it's a very generic standard. It just defines basically you have a Sparkle query language, you have RDF, you have some ontology in OWL. How can these things be combined? And what it basically allows for is that your query returns all of the solutions under entailment of some entailment regime, which could be, for example, OWL. So if you query Sparkle, by default, it just returns data from the RDF graph. With this entailment regime, you could also get solutions that are entailed through OWL entailment from your RDF graph, from your data. Yeah. So this is a cool feature, but it's very hard to implement. Yeah. So it states how entailments can be included in Sparkle results. There's support for RDFS and sublanguages of OWL. It's not well supported, unfortunately. There are some coverage maybe of RDFS in some engines. So I'm not going to go into too much detail on that, but it's something still, that requires more research, more investigation. In fact, there's some even open theoretical questions about whether OWL2DL, which was the final decidable language we saw in the course, whether it's even decidable to answer things like Sparkle queries over OWL2DL languages. Yeah. So the decidability is still open as far as I remember, as far as I know, for answering queries over over entailments under Al2DL. So I'm not going to go into it in too much detail. If you're interested, you can check out the book chapter in the book that I uploaded at the start of the course, or you can have a look at the specification. But basically, it provides this formal framework under which you could write a Sparkle query and get answers that are not only explicitly in the data, but that could implicitly hold through an entailment of OWL or the FS or whatever it might be. It's just very hard to implement efficiently. So that's why people are reluctant to do that, especially on the web. Very briefly, if you're a web developer, there's some new output formats that are quite nice. The original formats, I believe, were just XML, which nobody really wants to work with anymore. So you can get from your Sparkle endpoint, you can ask for results, get select or ask results in XML, JSON, or CSV, TSV format, adding JSON and CSV, TSV to 1.1. So you don't have to work with XML anymore. And you can get your construct, describe, RDF data. These queries generate RDF graphs. You can get this in standard RDF syntaxes like RDFX, RDF XML, Turtle, Entrepose, in a variety of different syntaxes. So when we spoke about Sparkle being used to query data sets on the web, a very important feature of Sparkle then is the protocol. So imagine we did the query earlier and we said, okay, we're going to query linked geodata and we're going to extract the information about the embassies. So we just specified the URL. Yeah. For that to work, somehow Wikidata, which we sent the query to, needs to know how to communicate with linked geodata. What parameter does it use to send the query to it? Well, what should it use, get or should it use post? What kinds of HTTP features should it use? These things are defined in Sparkle 1.1 protocol, which follows a sort of RESTful kind of paradigm. Yeah. So it tells us how to issue queries or how to issue updates as well over HTTP, although many of the data sets that provide Sparkle endpoints will have disabled updates. You can just query them, they're read-only. Using get or post, how different output formats can be requested. So how you can say, oh, I want Turtle for my data, or I want XML, or I want, in this case, it would be, I prefer Turtle, but I can also accept RDF XML. Or you could say, oh, I prefer JSON, but if you don't have that, I can work with TSV. This is called content negotiation. What response code should be returned? So for example, if you should return 200, okay, some 4xx problem if the Sparkle query is invalid, or some 5xx problem if the query is okay, but the server failed to answer because the query was too expensive or the server was too busy or what have you. So the protocol defines all this. It is, if you kind of understand a little bit about web architecture and so forth, it's pretty standard. It's what you would expect. There's nothing too crazy here. It does create some problems though. For Sparkle engines, it's not so easy to implement this sometimes. A classic case is that when you're generating results from a Sparkle engine, oftentimes you'll want to generate results one by one. Yeah. So the problem with these codes is that you need to sort of report them as part of the header before you start reporting the content. Yeah. So what would be very useful would be a feature where you could say the code is I think there's a 201, which is partial content, which is I didn't return you everything, but I returned you part of the thing you requested. But you don't know at the start if you're going to be able to return that or not. You don't know if you're going to return all the results or a few of the results. So there are some complications because you have to issue the code before you start returning any results. There are various kind of complications associated with this. So often endpoints will have to load all of the results, buffer them, and then see if they got everything, and then return the response code, and then dump all of the buffer to the clients. Yeah, so some technical issues. Okay, so we have Sparkle endpoints on the web. We can see again our example. We spoke about this in the start of the course. Where are we? Sure. So, didn't work. Okay, that's fine. URL was too long. Let me grab it here. Here we go. Here's a query. We're querying for, if you remember the example from the start of the course, which was the Nobel prize winners in literature who fought in wars, the year the war started, and the year they won the award. So we can run this using Sparkle over Wikidata. We can run this Sparkle query, which gets awards received. The award received was a Nobel Prize in literature. Then we get the point in time when the award was won, and then we extract the year from the date. Let me zoom in a little bit, sorry. Then we check to see that the person who won, they were involved in some conflict. Now my autocomplete's gone. We get the name of the conflict. We get the start time when the conflict started. We bind the year of that as war year. Then we get the name of the person who won the prize, Nobel Prize. We filter and we make sure that the war name is in English and the laureate name is in English. We could change that to Spanish or whatever else we might like to put. And then we order by the award year. So we order them according to when they won the award. And we get some results here. We get Salik Patron, 1870, won the award in 1901. Henrik Sienkiewicz, it's a bit hard to pronounce his name, 1914. Carl Spittler, Winston Churchill, Ernest Hemingway, Albert Camus, Jean-Paul Sartre, Mikhail Sokolov, Samuel Beckett. We have somebody from Ireland here, Heinrich Boll, and so forth. William Golding. No Chileans, I think, no. Camilo Jose Sella, do you know? Does anyone know? No? Claude Simon? No. No, they're, yeah. So we get our results. So anyone can go on the web. They can go query whatever they want. Sometimes it will give you timeouts. It doesn't work perfectly all the time. Sorry, share screen. Let me swap. So it doesn't work perfectly all the time. Sometimes it will give timeouts. So it will tell you that your query is too expensive and can't be run in a minute, which is understandable. The service processes in the order of millions of queries per day now. So there's quite a few applications that are built on top of this Sparkle endpoint. Okay, that's it. Sparkle. That's the Sparkle section. Any questions? Thoughts? Okay, so what's coming up in the course? I think tomorrow is the deadline for the reading group peer reviews. Yeah, so just be sure not to change the format of the JSON document because we're just going to take all the JSON documents and compile them to compute the scores. Also be sure in your comment to say something such that it's kind of clear that you saw the talk. Yeah, so the first few times we did this, we got siete excelente in about 25 of these evaluations. And so we would ask you to add a comment that really makes clear that even if you don't, it doesn't have to be a negative comment. You can just say, oh, I really like the part where same thing. It doesn't take too long. Hopefully, in any case, I guess 5 talks and they're about 5 minutes each. So it shouldn't be an overly taxing job. The idea would be to see some of the other talks and to get some ideas of what the other research talks are out there. Of course, if you want to watch more talks, that would be excellent. That's highly recommended to watch more talks. Yeah. On Wednesday, today is the deadline for uploading project ideas, I think. So, yep, we'll go through those as they come in and we'll say, oh, this sounds good, or maybe better, this is too much, or this is too little, or it would be better to add some. So we'll add some suggestions along that as well. On Wednesday, we'll have the Sparkle 1.1 lab. So that'll be the last lab on Sparkle. And then we have 2 more topics to cover. I'm not sure in which order we do them actually, but we have validation, which would be with Shackle. And we have linked data, which talks a little bit about putting all this on the web, which we saw a little bit of that at the end of this class as well. Questions, doubts? No? Okay, so see you on Wednesday.